Thank you. Good evening, everyone. Since time is short, Nandini told me more than what I want to hear about myself. So let me get into my presentation. When I started remote sensing, like early 1990s, the single dot in the image you are looking here, most of you are familiar with these high-resolution images. That single dot used to be 1 kilometer resolution, 1 kilometer by 1 kilometer resolution, and 3-4 spectral bands, right? So that technology in last 25 years has improved in all three dimensions, spatial, spectral, and temporal, leading to large-scale collection of these images, what we call global Earth observations. And the idea here is to use these global Earth observations to monitor resources on the Earth, whether those are natural resources or critical infrastructure like this. Nuclear power plants or thermal power plants, or identify where nuclear proliferation is happening throughout the world, especially in countries which don't have sufficient controls. So being at National Lab, those are the global scale problems that we looked at. After coming to NC State, everything scaled down to local, right? Oak Ridge has one of the world's largest, most powerful supercomputer, where I have my laptop after coming to NC State. So my problems now are local, but local is going to be new global, right? That is where I'm working on. So this diagram actually captures what kind of improvements happened from, let us say, 1970s, 80s, 1 kilometer resolution to sub-meter resolution that everyone can buy. So the only restriction is if you are asking for very high resolution image below certain resolution, there are restrictions if the data you are requesting from United States. But if I ask, I want sub-meter resolution from Afghanistan, next day FedEx will deliver me a lot of data, right? So there are certain restrictions. You cannot peek into your neighbors to look at that high resolution. But with drones, I don't know how that is going to pan out. Ordinary citizen can now buy sub-meter, 50 centimeter resolution images from private companies, which typically used to be big federal agencies like NASA, for example, or Indian Space Research Organization, or European Space Agency. But things has changed a lot in recent years. A lot of things are privatized. So my research, as Brian mentioned, is a subfield of AI, especially machine learning, meaning how to mimic the learning problems using the computer. So for example, if you look at this image, if you look at this image here, so those circles we know that not made by aliens, right? Those are happening because of, someone said I made a lot of jokes, so that's why I'm trying to make jokes. But so these are like the way we do irrigation, right? So that is resulting in these circles. But the image here is telling the complex relationship between food, energy, and water. So for example, if you go to Texas, pumping water is free. You don't have to pay. But each farmer end up paying millions of dollars for power systems, right? How can you use AI and these global Earth observations? So for example, to predict to the farmers what is ET going to be next 1 week. Then you can schedule these irrigation systems to conserve not only water, but also you are giving water to the right place or right crop, which is under stress, right? So right now, but we are not doing that. We are still not there, but we are getting there. If you look at these figures, we know why this field is so important that everyone should think about more closely. Agriculture accounts for 70% of total global freshwater withdrawals, and food production supply chain consumes about 30% of total energy. Now, fast forward, another 3 billion people are going to be there in next 30 years. So that means 60% increase in food, 50% energy consumption, and 10% increase in water usage. So these are big numbers, right? So right now, and there are a lot of other challenges, food waste, and we are dealing with diseases, and climate change is going to impact these. So it's not just increasing food production, but increasing or doing agriculture in sustainable way using modern AI kind of methods. So, and why we are interested in this field is because a lot of things happen, right? When you plant something, you expect yield is going to be this much, but in between something comes up and happens something like, can anyone identify what this is? Why this is happening? So these are exactly two images, same location. You can compare, these are rivers, and these are different colors represent different types of crops. But if you look at the pattern here, something happened. Damage happened. Can anyone guess why, what kind of damage this is? Flood is good guess, but flood is water. Water looks like blue. So this is hailstorm damage, right? So you don't expect this, but you want to identify, this is one kind of damage, but other damages could be insufficient water, like drought kind of conditions, or insufficient water, or let us say crop diseases. And for these kind of things, you cannot wait till a satellite acquires and that data is dumped into Eros data center, and they will take their own time, give you satellite image after 1 month, and I take my own time, analyze, and tell something happened, right? By the time entire crop got disease, because of diseases or some other problems, crops get destroyed. And right now, the analytics or AI is moving towards real-time analytics. I will give some of those examples. From static analysis, which we are doing for last 30, 40 years, now we are trying to do this in real time to identify these problems. So here is an example, drought conditions. And this is another interesting example. So this slide shows several problems. So USAID spent about $7 billion in Afghanistan, especially for supporting farmers to grow wheat, but they are still growing weed, right? Helmand provenance accounts for more than 70% of opium production in the entire world. One provenance accounts for 70% of production. And where that end up? Probably here in our local schools, right? So, but how do you find these complex things where we don't have access to the ground truth? How do you build a machine learning model? Like, for example, you talked about Google Brain project. So you are giving examples telling that these are cats or these are dogs, right? You are giving examples to computer to learn, but I don't have any ground truth, right? So I cannot go to Afghanistan to get the ground truth. And in fact, we collected ground truth, but those are soldiers sitting on their Humvees and telling me this is opium field. But the XY coordinate is on the road. And I don't know whether they are looking here, right? So how do you deal with those uncertainties to build your models? That is also part of our research to identify these kind of things. And machine learning for remote sensing or image understanding has to go through various stages. So this broadly tells starting from feature extraction to applying machine learning model using supervised ground truth data supplied by experts, and finally producing a map, like these are different types of crops. And that kind of maps are important for understanding various things. For example, where the crops, how the crops are distributed and what is happening. So for example, next slide I will show is the changes are happening for a lot of things. Like, for example, DOE has Office of Biomass has a policy called 2030, where the objective is to replace 30% of fossil fuel consumption by biofuels by year 2030. That's why it is called 2030 policy. But changing 30% of fossil fuels with biofuels is not easy task, right? Existing biomass does not support 30% of fossil fuel generation. So as a result, in Midwest, if you go, it is becoming continuous corn production. And if you go to, let us say, South America, especially Brazil, they are growing more sugarcane fields, right? So we are building a framework, which is shown in next slide, building a framework to identify where the changes are happening by monitoring every day's crop signal. So this shows, this image shows the entire workflow acquiring from satellite image, doing all pre-processing, generating time series signal, and characterizing what kind of crop this is, and identify if there is a change in that kind of pattern as compared to previous years. So which is shown here. So for example, this framework allows you to find things like this, if there is some kind of damage happened, so like this, or if there is a change in pattern. So this is C stands for symbol corn, S means soybean. So if you look at here, this is to be crop rotation, corn, soybean, but now it is becoming continuous corn production. So this framework allows you to find these kind of changes, but the challenge is this data is huge, right? Even at 250 meter resolution, MODIS data, which is very coarse resolution, everyday data, you are looking at each tile. This is the one tile, one image product. You are looking at 23 million time series. And at the global scale, you are looking at 10 billion time series. And you have to process all those to predict if there is a change today. Now, change that, and now think about we have half-meter resolution images, right? And that leads to 150, we are looking at land surface of 150 million square kilometers, which translates to 600 trillion locations. So these are all time series, and each time series, each point is a multispectral value, and you have to analyze the data to identify these changes, which is a big challenge. And so to address these problems, I don't want to throw all the math, but we looked at semi-supervised learning, where you can combine labeled and unlabeled data. We looked at deep learning, which already was mentioned here, which requires, of course, a lot of examples, like big data and a lot of computing power. But this slide, I want to conclude by saying we are moving from those big iron to a nail. So for example, when I started on wax 11 by 780, which used to be from there to here, which is less than a teraflop. Now I have teraflop computing power on the credit card kind of chip. So the idea here is, and it takes only 15 watts power consumption, so I can put this small supercomputing device on board a small UAS or drone, and as the drone is flying, I can analyze the data and identify if there are any stress. For example, if you look at this is NDVI image acquired by devices like this, and while flying, I can analyze the data and see there is some problem here. So that bright green spot corresponds to weed here, right? So we can, as it is flying, we can identify these. So, and the processing this at globally, local processing, but across the global is challenging because fields doesn't look same way as we are looking here. Like this is in United States, but if you go to other parts of the world, the field size is much smaller and different types of crops. Here, most of the crops are homogeneous. If you are driving from Minnesota to Iowa, you don't see anything except corn, right? Big corn fields, but that is not true. Even the scenario changes when you are walking in India, one crop to other crop, just while you are walking, not driving at 80 miles. Still nothing changes here. So this is a challenging problem, but things are better now with invention of these devices as well as improvements in computing technology. So if you put all of these things together and put AI on top of it, what you can do is smart agriculture, which is because we cannot increase the amount of landscape, right? That is fixed. What we can do is try to improve per hectare yield, right? By consuming less water, but improving the yield. So we can do that using, or we are getting there by using a lot of this technology, improved crop seeds, etc. So with that, I will stop and ready to take questions if allowed.